Alright, this is our third video on atomic structure and electron configurations, and now we're going to take a look at ion formation. Now, since you've been through pre-AP chemistry already, I'm hoping that this will make more sense to you this time than it did the first time. Ions are formed when atoms gain or lose electrons. So atoms gain or lose electrons to obtain a noble gas configuration. That means they want 8 valence electrons or an octet. Except for helium, remember, helium only has 2 valence electrons. So if we have an element that is closer to helium than any other noble gas, it's going to try to get 2 valence electrons instead of trying to get 8. Metals lose electrons and become positive ions called cations. Don't forget about this. Metals tend to be cations. They tend to make cations. And cations are formed by losing electrons from the highest energy level or shell. Nonmetals gain electrons in order to become negatively charged ions, which we call anions. Anions are formed by gaining electrons into the highest energy level or shell. So let's look at a couple examples. The calcium atom, if you look at calcium on the periodic table, it has 2 valence electrons. It's got 20 protons and it's got 20 electrons. That's what the calcium atom has. 20 protons, 20 electrons. And its electron configuration is going to be 1s2, 2s2, 2p6, and then 3s2, 3p6, because it's in the 4th energy level, 4s2. And our Lewis dot structure, because it only has 2 electrons in the 4th energy level, it only has 2 valence electrons, we're just going to put Ca and draw 2 dots. That's the Lewis structure for a calcium atom. Calcium ion is different than the calcium atom because it's going to lose those 2 valence electrons so that it will have an outer shell, 8 valence electrons. So the new valence electrons are that 3rd energy level. It's easier for it to lose those 2, so it ends up with 8 than to gain 6. So we'll end up with 20 protons still, because it's still calcium, but we have 2 fewer electrons, which makes 18. Our new electron configuration would be 1s2, 2s2, 2p6, 3s2, and 3p6. That's the new electron configuration, and now we have 8 valence electrons. By the way, the calcium ion Lewis structure is just Ca. There are no dots shown because we just gave up those valence electrons. We've got a 2+ charge. We show it this way to indicate that it lost electrons instead of gaining them. The chlorine atom, it's in the 3rd energy level, 3p, 1, 2, 3, 4, 5, 3p5. So let's write the electron configuration first. It's going to be 1s2, 2s2, 2p6, 3s2, and then 3p5. The chlorine atom has 2, 4, 4 plus 6 is 10, 6 plus 2 is 8, 9, 10, 11, 12, 13. It has 13 protons, and we could check that with its atomic number. Chlorine has, oh, I messed up somewhere, has 17 protons. 2, 4, 10, 11, 12, 13, 14, 15, 16, 17. Yeah, I don't know what I did. 17 protons, and it has 17 electrons. And Cl has how many valence electrons? It's that highest energy level. And the third energy level, we have 2 plus 5 is 7. If I can add correctly, 1, 2, 3, 4, 5, 6, and then 7. Got 7 dots. But then our chlorine ion is going to be different because we want to get to 8 valence electrons. I hope that you can notice that since I have 7 valence electrons, it's going to be really easy for us to just get 1 extra electron. That's a lot closer to a full energy level than giving up all 7 of them. So we're just going to gain 1 extra electron. We'll have 17 protons still, but this time we're going to have 18 electrons. 1s2, 2s2, 2p6, 3s2, and then 3p, we're going to have 1 more, so 3p6. Now we have a full valence shell, 8 valence electrons. And we show that with our Lewis structure. I'm going to draw it down a little bit to avoid confusion. Cl, 1, 2, 3, 4, 5, 6, 7, 8. It has 8 dots, and it has a -1 charge because I got 1 extra electron. You notice that the chloride ion and the calcium ion have identical electron configurations. That's because the electron configuration does not take into account the number of protons. It is only looking at the electrons. And they have the same number of electrons, but because they have different number of protons, they're different elements, and they're going to have different charges as well. Look down here, noble gas configurations and the Lewis dot structure of the following atoms and ions. Go ahead and pause the video and try a couple of these. All right, Fe, 1s2, 2s2, 2p6, and we are going to skip past all of that stuff because we're doing noble gas configurations. I'm going to start with argon because it's right before iron, so Ar, and then 4s2, 3d6. Ar, 4s2, 3d6. Well, there's my ground state configuration for the iron atom. You notice I don't have a charge here, so that's the atom. This one has a charge, that's an ion. And because it's a positive charge, I have 2 fewer electrons. So I'm going to lose 2 electrons from, this is kind of tricky, watch out for this, I'm going to lose 2 electrons from the highest energy level. That can be kind of tricky. Ar, and then I'm going to lose electrons from here because that's my highest energy level. It's just going to be Ar 3d6. Okay, Fe3 plus. Ar, well, we lost electrons from that highest energy level first. And then I have to lose 1 more electron, so it's going to be 3d5. This is an AP level concept. You guys did not do this in pre-AP chemistry. But you need to know that we will lose the highest energy electrons first when an ion is being formed. And we gain the highest energy electrons when an ion is formed as well. So oxygen atom, let's look at that. 1s2 would be helium, but we're going to just start with helium. Helium, and then 2s2 and 2p4. Two S2, 2p4. Well, I want to gain enough electrons to get to 8 valence electrons. Well, actually it says right here, 2 minus. So it would be He, 2s2, 2p6. we have an example on the AP test that we want to go through now, where you're writing the electron configuration for the valence electrons of tennessine. I want you to pause it and try this. I think you might be surprised at what the answer is. All right, I'm going to go through the answer now. Here's what throws students off. It says write the electron configuration for the valence electrons of tennessine, and they read that and they think noble gas configuration. That's not what they asked for. They asked for the valence electrons of tennessine. So let's look at where tennessine is, which is TS. TS is way over here. It's element number 117. All right. So if we were to write the noble gas configuration, we would start at Rn, and then we would go 7s2, then we would go 5f14, 6d10, and then we would say 7p5. But that's not what it asked me to do. It said to write the valence electrons of tennessine. So I'm only going to write the electrons that are in the highest energy level, which is 7s2, 7p5, because 7 is the highest energy level. It's a tricky question. They're not asking for the noble gas configuration. They only want the valence electrons. So watch out for that. There's a difference between asking for the valence electrons and the noble gas configuration. All right, we have one more page. Let's try to wrap that page up, and then you can move on to the practice related to this. Effective nuclear charge and shielding. I want you to be careful with the word shielding, especially when you're answering questions. The AP graders do not like to see the word shielding appear in your answers unless that is absolutely the correct explanation. A lot of students use shielding as kind of a catch-all way of answering a question, and they'll blame everything on shielding, and they don't really understand what it is. So the only time that you can use shielding as an explanation is if there are electrons in a lower energy level. Let's explain and talk about what shielding is. And honestly, I would maybe steer away from even using the word shielding and talk more about the effective nuclear charge. And that's what we're going to focus on in this section. The effective nuclear charge is called, or it's Z effective, okay? Effective nuclear charge, or ZEFF. It's the net positive charge that's experienced by an electron in a polyelectronic atom. Polyelectronic is just a fancy word for saying we've got more than one electron. The term effective is used because the shielding effect of negatively charged electrons prevents electrons on higher levels or sublevels from experiencing the full nuclear charge of the nucleus due to the repelling effect of inner layer electrons. So let's break it down a little bit more. Electrons that are inside, that are the core electrons that are closer to the nucleus, they have the same charge as any other electrons. Well, they tend to kind of hog some of that attraction to the nucleus, and they shield electrons that are further out from being able to feel the force of the nucleus. They also have an impact because we know that like charges repel. So those inner electrons repel the outer electrons. That's basically how shielding works. Shielding refers to the core electrons repelling the outer electrons. which lowers the effective charge of the nucleus on the outer electrons. Hence, the nucleus has less grip or pull on the outer electrons as it is shielded from them. That's what shielding really means. It means the outer electrons don't experience the same effective nuclear charge, or the same Z effective. They're not feeling the same pull from the nucleus that they would if they were in a lower energy level. If an electron is far from the nucleus, then many of the outer electrons will be between that electron and the nucleus. Hence, the electrons in between electrons of interest and the nucleus cancel some of the positive charge of the nucleus, thereby decreasing the attractive interaction between the nucleus and the electron of interest. So that outer electron, some of the charge from the nucleus that pulls it in toward it is canceled out by the repulsion of electrons in a lower energy level that kind of gets in the way. As a result, the electron further away experiences an effective nuclear charge that is less than the actual nuclear charge. Actual nuclear charge is just the number of protons, but what it's experiencing is reduced because there are electrons in the way on the inside. This effect is called electron shielding. I know there's a lot of words and a lot to take in. Here's kind of a picture that that isn't just kind of a, I don't know, a meme of how shielding works. You see this little cat down here that is pushing out the other cat and not letting it get to the milk. Okay, so it's like the inner electrons are pushing the outer electrons away so that they can't experience the pull of the nucleus. That's basically what shielding is. This is how shielding effect works. It's just a metaphor or a meme. Okay, this graph, it shows the relationship between atomic number, Z, and the effective nuclear charge, which is Z effective. Notice that atomic number is Z, effective nuclear charge is Z effective. That means it's being canceled out by some of the electrons in lower energy levels. That is experienced by the valence electrons of elements of the first 3 rows of the periodic table. So it's just focusing on 3 rows: hydrogen, helium, lithium, beryllium, boron, carbon, and so on. You notice that the effective nuclear charge is gray, and the purple bar is the atomic number. So the atomic number increases every time. It always increases as we go across, as we increase the atomic number, right? We're going through each of these elements. We're just going up 1 atomic number. So the atomic number is always going to increase. But what about the effective nuclear charge? Trying to erase that. The effective nuclear charge doesn't always increase. You see that it decreased right here. Then it increases, and then it decreases right here. And it increases. Where is it decreasing for the most part? I hope that you can kind of tell when it decreases, that's a new period. Both of these, this where lithium is and where sodium is, it's a new period. So the shielding effect occurs when there's a new period or a new energy level. It's further out and there is a layer of electrons underneath it that prevents it from feeling the full pull of the nucleus. So shielding really is only effective in explaining differences in the periodic trends and things of that sort when we have a new layer of electrons, when we're in a new energy level. Z effective is always less than Z except for hydrogen. That's one thing you can note. Z effective increases as you go across a period from left to right. And the number of core electrons shielding the nucleus from the valence electrons stays the same. Let me say that again. I'm not sure that it really clicked. So we're talking about how Z effective is impacted as you go across a period in this bullet. The second bullet point is going across a period, going from left to right. So we said the number of core electrons, the number of electrons that are not valence electrons, the core electrons shielding the nucleus from the valence electrons, stays the same as you go across a period. However, the number of protons in the nucleus increases. So the effective attraction felt by the valence electrons also increases. Because all of the electrons in that layer feel that increasing positive charge pulling them towards the center of the atom until there's a layer of electrons under it. Okay, so as we go across the period, since there's not a new energy level, the energy level stays the same, so the shielding from the nucleus stays the same, but the number of protons in the nucleus increases and the effective attraction felt by the valence electrons also increases. They're feeling the pull of having more protons in the nucleus, so a stronger positive charge. Z effective drops back down as you go to the next period. It drops back down as you go to the next period. Remember, that means we're going to a new energy level. The number of energy shells between the valence electrons and the nucleus increases. That's why. Thus, the number of core electrons shielding the nucleus from the valence electrons increases. The number of core electrons shielding the nucleus from the valence electrons increases. So shielding increases only when you get a new energy level. All right? And this is why Z effective decreases. When you go to the next energy level. Or the next period, we could say. Just to sum it up, that's what we're saying here. That's why Z effective decreases when you go to the next period. All right, this is a new concept. It's important in explaining periodic trends, which we're going to be doing in the near future. Go ahead and try your hand at some of the practice problems, and I will see you next time.